Greetings all, welcome back. So one more aspect I'd like to talk to you about before we sort of move on beyond week one into week two, start looking at particular types of differential equations, particular structure within a differential equation, and look for methods for solution and such. And that is a tool that we use, what I want to talk about today is a tool that we use a lot of times when we just want to get a sense for how a differential equation is behaving, especially a first-order differential equation. You want to be able to see without doing a lot of analysis or calculation or something. Okay, so let's go to the whiteboard. So I'm going to share the board. I want to do some writing for you. Okay, now we're back here again. And what I want to talk about today is let's go back to our two differential equations. I want to compare those guys one last time. I guess that was an X. Hang on a sec. There's my eraser. This is dp dt equals p over 2 minus 450. These were the two differential equations that we compared. They're both first order, they're both linear. One basically on the right-hand side didn't involve the dependent variable at all. The other one did not involve the independent variable, so they had some pretty marked differences. However, notice that on the right-hand side here is that this is always something involving, in this particular case, it's just the independent variable x, but it would involve typically x and y. And this guy here, because we're looking at t as the independent variable, and we're looking at p as the dependent variable, this is something involving t and p. Okay. The reason for that, or that's what's useful for that, the reason why this is useful is that solutions to ODEs, first order ODEs, as a matter of fact, things change for looking at higher order stuff, and we'll get to that at some point in this class. Solutions to ordinary differential equations exist somewhere. They live in the xy plane, or sometimes in the other guy, the TP plane, the plane whose coordinates are the independent variable and the dependent variable, has graphs of functions. So, and what we'll be doing in this class, just like in calculus, what we'll be doing in this class is graphing solutions to differential equations and then looking at their properties as they relate to the actual differential equation. One of the tools that we'll use for this is this notion of graphing without actually graphing. So what does that mean? Suppose we have a y of x. Suppose we have a function which solves a differential equation, y prime equals some function of x and y. Okay. So we have a solution, right? Then, if we chose a point in the I keep doing this, I keep making a mistake here. If we choose a point in the xy plane that passes through the function, right? So this function y of x passes through x0, y0, because if I evaluate the function at x0, I get y0. Okay, so that's actually true. Then I know by the differential equation y prime at x0, its derivative at x0 is going to be precisely equal to the right-hand side of the differential equation evaluated at x0 and y0. That's useful for us. I don't particularly like that little tail thing there. Okay. That's useful for us because I don't need to calculate a solution to know the slope of my solution curve at a point. So if I just wanted to understand how solutions behave at a particular, for a particular differential equation, and I have no idea how to solve it, I can still take a look at a point where the solutions live and calculate the slope of a solution curve at that point, and I can do that for a whole little grid of points. And if I do that for a whole little grid of points, I've created a field of slopes, also called a slope field. And a slope field is a way of basically getting a sense for how a differential equation behaves without actually doing or calculating a solution. Sometimes we can't. We can still get a sense for what's going on. So to do that, I want to switch slightly and draw for a second. So let's do this. Let's look at a function in the t, well, again, let's get rid of that guy. In the x, y plane, and I'll choose a point x0, and I'll choose a point y0, and I'm at this particular point, right? And I want to be able to say, okay, well, let's actually look at an example. Let's look at the example dy dx equals x minus e to the x over 2. That was a before in our comparison. So look at that guy, and I don't know how to solve it. I forget all my stuff about calculus. Well, I know some things about calculus, but I forget how to solve this particular guy or don't really know. But I can still say something about how solutions behave at a point because my solutions live in the xy plane. And I know the slopes because the differential equation can tell me that. So I can basically say, let's choose this particular guy at 2, and let's choose this particular value of y at 1. And then I can say dy dx, x equals 2, and y equals 1. Well, that is x minus e to the x over 2 evaluated when x equals 2 and y equals 1. Y is not in this particular guy, but that's okay. And if you calculate this, this is 2 minus and then e to the x over 2. That's e to the 2 over 2, so that's, I'll just write it out. This is 2 minus e to the 1, which comes out to be something like 0.718. Sorry. To minus 2.718, so this comes to be minus 0.718. Small negative thing. So I can basically come here and I can basically draw this guy in at that slope, and I know for a fact that that's what my solution looks like at that particular point. Okay? I can do this for a whole bunch of other points. And what I wind up with is a slope field. Okay, now what does that look like in practice? Well, I'm going to stop the share, but also start the share again and bring this guy up. This is a website. And on this particular website, you can go to this website. If you just do a search for GeoGebra and then look for slope field, you can find this. And it would be worth it to start messing with it. But one thing you can look at is this is what's called a slope field, basically. And I've switched it. The original thing was e to the x plus y or something in a slope field here. But you can see that all I've done here, or all the computer has done, is calculated little slope fields. Basically just took for any value of x along the horizontal axis, stuck it into here, and realized for any value of y, they're the same. No matter what y, you notice that all those slope fields are the same vertically, right? They all have that same slope. But if I move over here, they're much steeper, but they still have that same slope. And even here, they get really steep. What this guy is a slope field, basically. It's a way of seeing how solutions behave without actually calculating much more than just the right-hand side, the f, basically. Why is that useful? Well, think of it this way. What a slope field might look like. It's also called a vector field, by the way, but what a slope field might look like. If you were in a forest, or you come down to a stream, you walk into a stream, fast-moving stream, and you look down at your feet, you'll notice, make believe that there's grass growing under the water in your stream, basically. The stream has a current. You'll notice that the blades of grass are all bent over because of the current, and the blades of grass are bent in precisely the direction of the current at that spot where the grass blade is growing. If you look at nearby grass blades, you'll notice that they're in a slightly different direction, but they're all sort of moving downstream, literally. You'll also notice that if there's a rock downstream, that the blades of grass tend to be bent in such a way to go around that thing. What those blades of grass are doing is they're displaying precisely what the current is at that particular place in the stream. And the nearby grass blades are almost in the same direction, but not quite. That's what this slope field is doing. It's giving you a sense for what movement is. It's giving you a sense for what the solutions look like. Now, if I were to make this thing as a higher density, sort of a clever way of doing this, go away. There we go. It's not behaving as well as I'd like. You can see that you get a better sense for what's going on and such, but either way. Now, here's the thing that's interesting. If I can find a curve that's tangent everywhere to this field, this slope field, I found a solution. And what this particular thing does is it evaluates a solution numerically. Now, it's something we'll look at in this class. We won't do much with that. We'll actually be calculating solutions because numerical solution producers do something a little bit different than actually solve differential equations. They fake it in some sense. But this would be a solution, the green curve passing through A of 2 and minus 1. Okay, the idea of what a solution curve. Our particular thing had a slope field here at 2 and 1. And at 2 and 1, you can see that it's negative. It's round, less than 1 down. So it's around minus 0.718. So you get some sense for what's going on. We're going to use slope fields. We're not going to be producing them very much because by hand it's kind of ridiculous to produce a slope field because it takes a lot of work. You don't get a lot out of it in some sense. But we will be using them. And this tool, this GeoGebra tool, is a very nice tool for doing something like this. So I'll leave you with this now. Let's stop the share. Come back to me. And again, there are a couple of problems in the book that have to do with slope fields. A matter of just recognizing when a slope field has a particular look to it. It's going to be useful to us. So take a look at those. And certainly let me know if you have any questions, but I'll leave you for now. Thank you very much for listening, and we'll talk again very, very soon.